So we've looked at different types of bonds, and now we have to see how do these bonds give rise to certain properties in compounds. So first, let's take a look at molecular compounds, which are typically between nonmetals. Remember, these are the ones that are going to have covalent bonds. The covalent bonds form the molecules which make up a sample of a molecular compound. So if we think about a molecule, typically they're not expected to conduct electricity. Why? Because your electrons are held in place in your covalent bonds, and in order to conduct electricity, you need either mobile electrons or mobile charge, none of which your molecule has available. So if we can kind of visualize this, here's like a linear molecule. So this would be a molecule which makes up a molecular compound, the smallest unit of a molecular compound. And the bonding electrons are locked in place. Even if I try to move it by itself, these are arranged in such a way that they are, according to VSEPR theory, these bonding electrons are as far apart as possible, which is why we have this particular 180-degree bond angle. And this bond angle stays fixed. It's a fixed bond angle because these bonds are fixed in place. We have fixed electrons, not mobile electrons, and that's why your molecular compounds do not really conduct electricity. If we go back, okay, another thing that your molecular compounds tend to have is a low melting point. If we think of diatomic chlorine, diatomic nitrogen, oxygen, those are all gases. Water, H2O, is a liquid. These are not typically things that have high melting points. They typically have lower melting points compared to the other types of solids like ionic or metallic. And this is actually because of IMFs. They have weaker IMFs, and we'll get into that more in another chapter, but you should know that these molecules, molecular compounds made up of nonmetals, typically low melting points. And even though we were just talking about small molecules like H2, like H2O, there are some molecules that are super large, made up of really long repeating chains called polymers. So really large molecules do exist as well. Okay, now let's get into ionic compounds. Ionic compounds are made up of ions that are attracted to each other, like Na plus and Cl minus. And even though we write the formula as like NaCl, it's actually in a sample of an ionic compound, millions and millions of Na pluses combined with Cl minuses in a crystal lattice. And it would just have the, a 1-to-1 ratio, but really there's millions of these ions present. And just to give like a better view, here's like a 3D structure. You have your positive ion here. It's completely surrounded by negative ions on all sides. So you're really maximizing the attraction between positive and negative. And notice that, the other purples are essentially as far apart as possible. You're minimizing repulsion too. So it's this really large 3D lattice where you're maximizing attraction, minimizing repulsion. And again, as I was saying, even though we write the formula as NaCl, these are really millions of positive ions, millions of negative ions, all in a lattice. And we write the simplest ratio when we're writing the formula, which we can also call the formula unit. So if it was a 1-to-2 ratio, like Mg, magnesium, Mg2 plus and Cl minus, then we would write MgCl2. But again, really millions and millions of these ions, all locked in this lattice. Now this lattice, because we have this attraction between ions, it actually takes a lot of energy to break this once it's formed. We have this strong attraction between millions and millions of ions. It's going to take a lot of energy to break this up. It also releases a lot of energy when it's formed because it's super stable. So we call the lattice energy, technically, the energy released when a mole of ionic solid forms from its gaseous ions, so like M plus, X minus coming together to make the ionic solid. Super exothermic because you're releasing a lot of energy. Remember, forming bonds is exothermic, releases energy. But a lot of times lattice energy is more thought of as the energy needed to break the lattice apart, because that would require an input of that same amount of energy that would have been released when making it. Now, stronger ionic bonds are going to result in a bigger and bigger lattice energy. The stronger the attraction between ions, the more energy needed to break up that lattice. So if we go back to chapter 7 and think, oh, what were those two factors that influence force of attraction, or Coulombic force of attraction? And that was distance and charge. Since we're talking about ions here in our crystal, remember just making sure that these are ions, Na plus and Cl minus, not atoms, NaCl. We can talk about charge. So greater charge would make a stronger force of attraction, greater lattice energy, and a smaller radius would make a greater force of attraction. This all goes back to Coulomb's law. That looks something like this. We said greater charge, greater force of attraction, smaller distance, greater force of attraction. And it makes sense if you think of magnets, putting them closer together, you feel that attraction more. If they had greater charge, you would feel that attraction more. Okay, and the stronger attraction, if you have a stronger ionic bond, it's going to not only increase the lattice energy, but it's going to cause a higher melting point. It would take a lot more energy to break apart that solid lattice to melt it. And it would also cause a much higher density because the ions can get closer together if they attract each other more. So if I kind of go back just to my picture, the higher the force of attraction between the ions, the less space there is between ions, and this can get more densely packed. So I've seen questions on the AP asking about density, and that's kind of the same thing as asking about how strong the bond is, how great that force of attraction is. So when answering questions about ionic bond strength, you're thinking back to Coulomb's law, greater charge, smaller radius. So a lot of times in a question, they might give you data, like if you see here, you see compounds and lattice energies given in kilojoules per mole. Here the lattice energies are positive because you can think of it as the energy needed to break up the lattice. And you might have to explain the data based on what you know about the factors that influence lattice energy. So look at this question. Why does LiF have a greater lattice energy than LiCl? Take a moment, try, and then check your work. So if I think about the two factors that affect lattice energy, charge and radius. So these both have the same charges, +1, -1, +1, -1. So I don't want to use charge as an argument, but I can use radius. Li plus in both. But here I have F minus versus Cl minus. F minus has less shells than Cl minus, so F minus is a smaller ion. And so if I have a smaller distance, I have a greater force of attraction, and therefore I have the greater lattice energy. So that's all I'm looking for. That fluoride is smaller than chloride. And I wrote F and Cl, but I really should have written F minus is smaller than Cl minus because it's the ions that are in these ionic compounds and not the atoms. So, simple, short answer to the point. Take a moment, try this example. Compare why, the Y is what I'm looking for, does strontium chloride have a much larger lattice energy than LiCl? Take a moment, try the problem, and then check your work. So again, the two factors would be charge and radius. So let's consider the first, charge. That would be a great explanation. Here Li is +1, Cl is -1, but here Sr is 2 plus and Cl is -1. So I have greater charge, and therefore we have a greater force of attraction. Sr2 plus has a greater charge than Li plus. Greater charge causes stronger Coulombic force of attraction. The other factor, radius, would not be a good argument to make here because strontium as an ion has a lot more shells than Li plus. So it's likely that strontium is a larger ion than lithium, and therefore that would have the opposite effect. You would think that if you have a larger radius, it would make the lattice energy smaller, which it doesn't. So that must mean that charge is the bigger factor and the influencing factor here. So make sure you choose the correct factor based on whatever the evidence is suggesting. Take a moment, try this example, then check your work, which has the greatest lattice energy. So I'm looking for greatest charge and smallest radius. They all have the same charge, +2, -2. But if I'm looking at my negative ion, my anion, I'd want to pick oxygen over sulfur because the oxide ion is smaller, has less shells. And out of all my positive ions, I'd want to choose magnesium because it also has the fewest shells and would be the smallest. So it would be choice B. Take a moment, try this example, and then check your work. The melting point of magnesium oxide is higher than that of sodium fluoride. Explanations might include which. Now notice these are both ionic compounds, so we're talking in terms of force of attraction of these ions. Oh, we're talking Coulombic force of attraction, explaining in terms of charge or distance. So anything that would make it have a higher lattice energy would also increase the melting point. So let's see, M22 plus more positively charged than Na plus. That's true. And that greater charge would cause a higher melting point. So that would be a great explanation. So yep, one would work. 2, O2 minus is more negatively charged than F minus. Sorry for the typo. That's true. And higher charge would also account for a higher melting point for ionic compounds. So yep, that would be great. And let's choose 3. O2 minus is smaller than the F minus ion. Ooh, be careful there because these are isoelectronic, and F, for the same number of electrons, F actually has more protons pulling that in, so it would actually be smaller. So this would not be a true statement at all. So I can't choose this. I would only choose 1 and 2. So make sure you're also choosing correct statements for this. Okay, now let's just get into some properties that result because ionic bonds are super strong forces of attraction. That's going to result in really high melting and boiling points. They're usually in the solid state. Think of sodium, table salt. It's a solid. Even if you dissolve it in water and then try to boil off the water, the salt gets left behind still as a solid. And they also have very low vapor pressure, meaning if you put it in a closed container, very little vapor is going to come off of that solid, which makes sense because it's such a strong force of attraction. So why? Very strong attraction between ions, and not just two ions. Remember, there's really millions and millions of these ionic bonds between this crystal lattice that you would have to break up to melt or boil it, turn it into a liquid or solid from this solid. Turn it into a liquid or gas from the solid. So that's not really going to happen very easily. It would take large amounts of energy. So that's why it has very high melting and boiling points, especially when comparing it to something like a molecule. Okay, the other property you do need to know is about conductivity. So when you have these ions locked in a lattice in the solid phase, you do have ions, but they are not mobile. They are in a fixed location. And remember, to conduct electricity, you need mobile electrons or mobile ions. So an ionic solid cannot conduct. However, if you were to melt it, if you were able to put enough energy to melt it, or if you were to take that solid and dissolve it in water, because we know ionic compounds typically tend to dissolve in water, then it can conduct. So it conducts only in the liquid or aqueous phase, not the solid phase, because in a solid phase, the ions are stuck in a lattice. In liquid or aqueous phase, you've unlocked that lattice, and now these ions are free to move. And when you have mobile ions, you can conduct electricity, which is really just mobile charge. Okay, last property of an ionic compound, AP loves to ask about it, is something called cleaving. Ionic compounds are actually super brittle, meaning they break easily. They are not malleable or can mold into shape like a metal. And the reason being is you have your positive and negative locked into a lattice. So ones represent positive ions, 2 represent negative. And this lattice, remember we said, maximizes attraction and minimizes repulsion. So if I put any stress on this, one of these planes, one of these layers can easily shift. Okay, and then what happens is all your like charges line up. And what happens when you have like charges next to each other? They immediately repel each other, and a whole layer can break off. So this is called cleavage. So due to the repulsion of like charges, a whole layer can be cleaved. And so ionic compounds can break apart along smooth, flat surfaces where one of these layers just breaks right off. And this makes ionic compounds very brittle, not malleable. You can't mold them into a shape. So make sure you know all these properties of ionic compounds. They have these lattices, high melting points, super brittle solids that can be cleaved apart. They conduct electricity only in liquid or aqueous, not in the solid phase. Remember, molecular is not going to conduct at all. Ionic only in the liquid or solid phase, liquid or aqueous phase. And they also have a strong electrolyte behavior. When you put it in water, it tends to dissolve and break up into ions. Sometimes you might see structures or be asked to draw a Lewis structure of an ionic compound, and that's something you should be able to do. We're not going to have those lines that we see in molecules because you don't have the covalent bonds. We're just going to show the attraction between ions. And remember, we show ions with brackets and a charge outside. So all you're going to do for monatomic ions, something like Mg and O, making magnesium oxide, is you're just going to draw each ion in brackets. The metal, you're going to put no dots. Like magnesium would normally have 2 valence electrons, but we're going to show the loss of those electrons, and therefore, even though it has 8 valence, we're showing the loss of those outer 2, so we're showing no dots. And your nonmetal is going to gain electrons. O used to have 6 valence, now it has 8, so we're going to show all 8 dots and the charge outside of brackets. Now, sometimes the positive ions, since it doesn't have any dots, they omit the brackets and just put the charge, but I tend to put the brackets in. Okay, and then you're going to have enough of each ion so that your charges cancel because your overall ionic compound has no charge, it's neutral. And that's why we have a 1-to-1 ratio for magnesium and oxygen because they have equal and opposite charges. Try MgBr2. Notice there are 2 Brs needed to cancel out the charge of Mg. Mg has a 2+ charge. We show no dots to show the loss of electrons for this monatomic ion. And there's 2 bromines, not just 1, but each of them has a 1- charge, which is why I need 2 of them, because right now 2+ and 1- don't cancel. Where should I put the other? Would I want to put it right next to the other Br? Probably not. They repel each other. So I'm going to put the other bromide on this side. And notice now 2- and 2+ cancel each other out. Take a moment and try drawing the next one. Okay, so Na2O, I would need 2 NAs. I'm going to put them on opposite sides of an oxide. The oxide would have a 2-, and now 2- and 2+ cancel each other out, which is why I need 2 sodiums for every 1 oxygen or every 1 oxide in the formula unit. Take a moment and try drawing these Lewis structures. Now for these actually contain both ionic and covalent bonds. I have this polyatomic ion, NH4+, and within that, I'm going to have covalent bonds between the nitrogen and the hydrogen, polar covalent bonds, and that's why I'm showing them as these lines. Now, the Br- is now going to be ionically bound to the ammonium ion, and then these together can form a lattice of millions and millions of them really in a 3D structure, having all the, properties of an ionic compound. But, you actually do have both covalent and ionic bonds in this structure. And the same for sodium hydroxide. You have a covalent bond between the O and the H in the hydroxide ion, and then the Na+ and hydroxide are actually covalently bonded together. The last category, remember we had learned about metallic bonds, and that's what's actually holding a metal together. So even though we think of a metal like Na, we just write the formula Na. It's really millions and millions of sodium atoms, all in this crystal lattice kind of again, that are all metallically bonded together. And your sodium atoms or metals, they have low ionization energies. They tend to lose electrons easily. So what happens is the valence electrons become detached and float freely through this crystal structure. And it creates what's called a sea of mobile electrons. And having mobile electrons like this gives rise to a lot of different properties for these metals. And make sure you watch this video next. It's really great in giving a great visual as to why metals have certain properties, like why they are malleable. It's because of this sea of mobile electrons that allows it to be malleable. The sea of mobile electrons allows it to be a good conductor of heat and electricity. It gives it luster. It makes it malleable, meaning it can be molded into a shape. It makes it ductile, meaning it can be pulled into a wire. So do make sure you watch that video next and make sure that you do know these different properties and can explain them because these are on the AP exam as well. One other thing about metals is instead, in place of all one metal, you can actually put in metals together in that metallic bonding and create something called an alloy. So they can retain the sea of mobile electrons, it can retain this metallic bonding, but it doesn't have to all be the same element. And there's 2 different ways this can happen. One is called an interstitial alloy. So an interstitial alloy is when you have atoms of different sizes. So let's say you have something like iron, which is much larger in radius than carbon. What happens is the iron maintains this lattice or this crystal structure, this crystal lattice of metallic bonding. And the smaller carbons fit in the spaces, as you see here, between those atoms. And we call those spaces interstitial spaces. So this is actually called an interstitial alloy. So again, it forms when atoms of different radii participate in the metallic bonding. So the smaller atoms actually fit in the interstitial spaces between the larger ones. This happens in steel. Steel is a alloy of iron with carbon, and it actually makes the whole lattice harder and stronger, which is why they use this in steel. It also tends to make it more rigid and less malleable, less ductile when you create an alloy. Rather, if you took out the carbon from the interstitial spaces, iron would be a little bit more malleable than if you had it with the carbons in the interstitial spaces. So this is one type. When you have different size radii, you get interstitial alloy in the, fitting in the spaces in between. If you have comparable size radii, then you could literally just take out one metal and pop in another. And you're literally substituting one for another, so we call that substitutional alloy. So this is when you have atoms of comparable size, comparable radii, and usually no more than 15% difference, and one atom just substitutes for the other. This happens in brass. That's when you mix, get copper with zinc. And again, it still also makes it less malleable, less ductile than pure metals. And when you do this, your density will lie somewhere between the two metals that you're mixing. So you should know these two different types. The AP asks about the two different types. Substitutional, when you have comparable radii, one subs for the other. Interstitial, when you have a smaller one fitting in the spaces of the other. And here's just kind of a 3D visual of it. So make sure you know the different properties of molecular compounds. They don't conduct, low melting points, right? Versus ionic, conducts in the solid or aqueous, conducts in the liquid or aqueous, not solid. It's brittle and can get cleaved, high melting and boiling points. Versus metallic, malleable, ductile, conducts in the solid phase, and these different alloys that can be made.